This is the nozzle for a solid rocket motor. It's built from several materials, like graphite and linen phenolic, and it sits opposite the forward closure, which seals the end of the motor. The middle of the motor is filled with solid rocket propellant, the primary ingredients of which are ammonium perchlorate, aluminum, and an HTPB binder. The outside of the motor is 6061 1/8-inch aluminum, and a custom spin-cast thermal liner sits between the hot combustion gases and the thin case wall. This motor used 44 pounds of risky Batman rocket propellant, it ran for 9 seconds at an average pressure of about 500 psi, and it delivered a total impulse of about 46,000 newton-seconds, which makes the classification for this motor a P5200.
Oh man!
I told you it was good.
After firing, I used the horizontal bandsaw to cut the motor into various cross-sections. Before we look at these cross-sections in detail, if you haven't seen it already, my previous video covers the process of what it took to build this rocket motor. With that context in mind, let's chop these things in half and see what's inside. The nozzle and forward closure are the majority of what we'll be looking at. To gain a better understanding of each part, I'll use Onshape to show the assembly in a cleaner way. The throat of the rocket motor is made of graphite, which I'll show in blue here. The large section is phenolic, and the 2 O-rings on each side are made of high-temperature silicone and keep combustion gas from leaking out the side. The forward closure is in many ways a mirror image of the nozzle without a hole. Although this isn't really true, because we have a hole for an ignition bolt. This bolt in the center threads into the motor right before firing, and it's what allows us to transport the motor safely with no possible chance of ignition. Those of you with a keen eye will notice some discrepancies between the CAD and the real-life cross-section. The one that stands out most to me is the length of the throat of the nozzle. The throat is where all combustion gases converge and reach Mach 1 before expanding out the end. As designed, the throat length is 1/2 inch. I know that because it's in the CAD, but it's also on this t-shirt I made, which you can get in the description down below. How's that for a sneaky little merch plug? The 1/2 inch throat as designed does not reflect the actual cross-section. The length of this throat is almost 0. This is because of how the nozzle is machined and the, precision of how that happens. Longtime viewers will know I have a bit of a love affair with eBay lathes, and although I make my best efforts to use angle blocks and properly machine tapers, sometimes those angles don't come out exactly as I want. When machining the graphite, this 10-degree taper that I intended in the CAD likely came out closer to 8 degrees. And this 1/2 inch is a little something we call design for manufacture, which means that I know I probably can't cut an exact 10-degree taper, so I slightly oversize the throat, which has very little impact on rocket performance, and when I mess up and cut that 8-degree taper, we're still able to hold the same throat size. So the throat is made of superfine isomolded graphite because this stuff does not erode. This material is excellent at handling heat, and if you look close, you can tell that there are no lines here of debris or anything like that that's eroding the throat of the nozzle. We do have some slag deposits here. I believe this is mostly aluminum down here. This dimension between the graphite and phenolic can be challenging to get right. Because the phenolic erodes but the graphite doesn't, we have to have a step. That can either be a step up before the burn or a step down by the end of the burn. In my case, I opted for the latter. When machining the graphite on its own, I left a little extra on the inside diameter. Then, after seeding the graphite into the phenolic using RTV, I turned the remainder of that inside step down so the phenolic and graphite were flush before firing. This leads to a more efficient nozzle and ultimately higher performance. The O-rings on the nozzle held up great. So as a reminder, we have a primary O-ring right here and then a backup O-ring. We're trying to take all the pressure in here, which can be hundreds or up above 1,000 psi, and prevent it from leaking out through this path. This is a lot easier to do near the nozzle than it is at the forward closure, but the nozzle has a lower pressure than the forward closure does. It's a misconception that all pressure inside of a thrust chamber or solid rocket motor is the same. In fact, you can sometimes get a delta P or change in pressure along the length of the motor of up to several hundred psi. So it's easier to seal the nozzle end than it is to seal the forward closure end. In order to take a closer look at these O-rings and how sealing works in this whole assembly, let's put this under a microscope.
Oh my gosh, this guy's taking forever to move this microscope. Mr. Slowpoke over here.
Listen, while we wait, let me tell you about the sponsor for today's video, which is Henson Shaving. I am a dude who shaves almost every day, which might be hard to believe given I'm not exactly giving off hairy lumberjack vibes. But a clean, good quality shave for me makes a big difference. It's night and day. On a kind of personal note, Henson Shaving is a sponsor that I've wanted to work with for a while now because they have a history of being an aerospace machine shop. They made parts for the Mars rover and the International Space Station. Since then, Henson has gotten into the business of making razors, and at that, making some really good razors. We're talking high precision, extremely well supported blade, and instead of the expensive cartridges that some people are used to using, every double-sided blade for the Henson razor costs about 10 cents. I'm gonna tell you one thing, you do not get those types of prices in aerospace. Wow, he is still going. In the meantime, I can tell you that every blade sticks out just 0.0013 inches from the shave plane. And I know we've got some metric lovers in the house, that is 0.03 millimeters. That is nothing. That is crazy precision. Whether it's the all aluminum razor, the high precision, or the low cost, there's a lot to love about Henson Shaving, and I think you should give it a shot. You can do that using this link and the code BPS.space, and that will get you 100 free razor blades with the purchase of a razor. Remember how I said the razor blades were low cost? How about no cost for the first 100? You can check that out in the description below, and thank you again to Henson Shaving for sponsoring this video. And he's just about done. My goodness, takes forever. The first thing I want to look at with these O-rings is the squish factor we're getting here. These are size 431 O-rings, and they're relatively thick for the application. I deliberately pick the thickest size of O-ring I can because it helps us deal with deformations or imperfections in the material that we're trying to seal against. This setup with two O-rings back to back is a common one in amateur rocketry. Nobody's perfect, people make mistakes, so we have a primary, and then if the primary fails, we have a backup. But the secret here is we also have a tertiary seal. So the black part here is the liner material. This is the spin cast liner, and I hold it to a tight tolerance on this. It forms up against a barrier. Now, a lot of this gets messed up in the cross-sectioning process, so there's a bunch of gunk in here. But my goal was to actually create a tertiary seal. So this would be the primary seal, but the primary seal is not expected to perform super well. I load up this whole area with RTV, and then I just squish it down and assume it's possible that this becomes the primary seal, and then these two are a, first and then second backup O-ring. But the goal is to create as much sealing in this area as we can. The other area of interest here is the thermal liner. I want to know how it performed. In the previous video, we looked a little bit at the amount of erosion at this one particular section. This section sees some of the highest mass flux in the entire motor, which means it's going to strip away the most. We can see that erosion, but we can also see the char layer forming here. The char layer is what makes materials like phenolic and the mystery goo liner effective insulators. Through the inferno of a burning rocket motor, this surface converts itself into a hardened carbon layer. We can tell this is happening visually, but we can literally hear it too. This ends up being a fairly squishy material. I'd actually like to harden it up a little bit in future iterations, but you can see it's not hard for me to push my screwdriver into that material until I get to the edge. Just hear this? This is not a squishy material. It moves as one. That's because this is a char layer that's forming. This is a good thing. The char layer forms in the phenolic because when the phenolic resin breaks down through pyrolysis, or just thermal decomposition, it leaves a bunch of these carbon atoms, or amorphous carbon, on the surface. But the same thing is happening on the liner right here. It's just a little harder to see because the whole liner is black. But this, that's a nice char layer forming. See, you don't hear this, right? That's a soft material, and then you can hear this. So that's the char layer, that's that amorphous carbon forming, and that amorphous carbon contains a lot of air in it. It's like a very good insulator because we're trying to just keep the hot gas away from the untouched material right here. That's part of what makes this such a good thermal insulator. The last thing I'd like to look at is the interaction between the graphite throat and the phenolic carrier. I find this section very interesting, and here's why. A blade of materials like phenolic work because they give little bits of themselves off, and that carries away some of the heat. In the exit cone of the rocket nozzle here, you don't see much of a char layer. There's certainly some, but it's not that thick. Strangely, the char layer between the graphite and phenolic, where all of that RTV was, is much, much thicker. What I want to focus on is this. There's so much charring here, A, because we are burning away the RTV that used to be in this area. So this is sealed with room temperature vulcanizing silicone. And this all becomes so hot after the burn and a little bit during the burn, but really most of this is happening after the burn. So the graphite is holding all of the heat from literally like 45 pounds of propellant that have to squeeze through this nozzle. That heat has to go somewhere, and it's not just leaving out the nozzle, it's soaking into the graphite, which becomes red hot after the burn. The graphite is then going to burn away all this silicone. It's hot enough that the silicone basically has no chance. That happens through thermal soaking after the burn. And it's hot enough that it doesn't just burn the silicone, it's actually doing the same pyrolysis thing to the phenolic that we're doing when we directly interact with the exhaust gases. So you can see it pretty clearly here. I mean, obviously there's still a bunch of cracking, but all of this is basically what happens to phenolic when you char it, but the gas doesn't have a chance to escape. So it's soaking in a lot more of the material than it otherwise would, right? We've got this, which is exposed to high heat for maybe 9 seconds, and it doesn't see a whole lot. And then this section, which is exposed to high heat for, multiple minutes as this graphite cools down. The gas has nowhere to go. And those two contributing factors mean that this section just gets burnt to hell. This is one thing that makes me glad that I remade the nozzle for Simplex V2 instead of using the nozzle from Simplex V1. Originally, I had planned to use the nozzle from Simplex V1, and that would not have been a great idea because it's not unlikely that this same behavior would have shown up in the Simplex V1 nozzle, and I wouldn't have a great idea about that without trying to remove the throat insert. So while theoretically you can probably reuse nozzles for solid rocket motors like this, it is worth being aware of this phenomenon.
Moving to the opposite end of the rocket motor is the forward closure. Major parts here are the case wall, the thermal insulator, the aluminum closure itself, the hole for the HEI bolt, the pressure transducer for measuring chamber pressure, the O-rings, and the forward insulator. Like the nozzle, the closure is attached via radial bolts, which are easier to see on this side. And believe it or not, the forward closure, HEI bolt, and forward insulator are the exact same as Simplex V1. Even though that phenolic forward insulator is an ablative material, it still has plenty of life left.
This is not the pressure transducer that we used during Simplex V2. And I hope that's obvious because this thing is shot. This thing was from Simplex V1 and I took it out and it got very damaged in the process. The other thing we can see here is the hole for the HEI bolt. HEI stands for head end ignition, and it's the technique that I've been using to light Simplex V1 and Simplex V2. These are some of the worst tapped threads that I have ever made in my entire life, and I am sorry that you have to look at these because, man, it's very bad. I was a little concerned about this section right here. These two sections are pretty sporty in terms of how much aluminum we have to actually resist the pressure, and that's more a function of me trying to redesign this or remachine this to work with a 0.375 inch liner. But we should take a look at that HEI bolt. So this is the bolt post firing. The bolt still has the O-rings that are part of it. It still has the threads. This is made out of an M30 bolt from McMaster. It's a stainless steel bolt. It is extremely expensive, and I don't know why I committed to this approach, but you gotta commit to the bit sometimes. This is the exact bolt that also lit Simplex V1. What I did is I bored out all of the RTV and removed all of the crap from it, polished it up, turned a couple of new dimensions, and then used it on the second one. It's like an $80 bolt, so there's no need to buy a new one. All of the mess on the top here is basically what happens when you submit this thing to 5,000 degrees for 9 or 10 seconds and then just let it cook in here for a while. So this used to be a bunch of epoxy, and then on the tip here we had a bunch of aluminum that was coated in a pyrogen. The ignition leads, when they go through the bolt in this direction, they go through the bolt, they're sealed with a tremendous amount of RTV both on this side and actually mostly the sealing happens within here. This whole section gets filled with RTV, and the two bolts also have their copper stripped off of them at sections so that we are not trying to seal I don't know if it's Teflon or whatever the wire material is. We're not trying to seal directly against the wire material. We are sealing directly against the copper. These motors can operate at, multiple thousands of PSI of chamber pressure, and so we need to be real careful with how we make those seals. All right, we're gonna let this cool off. I'm gonna blow on it.
My little overhead camera here can't do more than 5 minutes of 4K recording at a time, and I think it's really funny that the most effective way to cool it down is just using a little compressed air. When I cut these cross sections, I accidentally cut a little bit past 180 degrees, which means that we have slightly more than a half circle here. That's kind of great in hindsight because it means we can screw things in, like the pressure transducer and the HEI bolt. I want to mention one more time how embarrassed I am of these threads. They are so bad. I don't know why I manually tapped this, but you live and learn, and the problem with living and learning on YouTube is everyone gets to see the learning part. Anyway, we have about 2 threads of engagement, maybe 1.5. Before Simplex V1 fired, I ran a bunch of calculations to determine the shear on the stainless steel bolt and determined it would be fine to fire with 1.5 threads of engagement, although slightly sporty, it wasn't actually a problem. And just like the nozzle and forward closure, the HEI bolt is sealed against the aluminum bulkhead here with 2 O-rings. One is a primary, the other is a backup.
Another thing to note here is that this is the finisil section. We have what's called a forward finisil in Simplex V2, and you can kind of see the artifacts of this. See, this section right here is a little bit discolored. This section right here is a little bit discolored, these two, and you can basically see just the start of a third discolored section. These are where the fins were, which means that these sections saw more heating than this section or this section.
Having a forward finisil like this gives you a bigger erosive spike, and I'm not going to talk too much about it because I feel like I keep talking about propellant erosion in every video. But when the throat diameter and port diameter are too close, you can erode the bottom part of the propellant. This high mass flux on the propellant wall strips it away faster, and it makes your motor burn a little harder on startup.
So mass flux is the thing that we're really concerned about, but not just for the propellant, we're also concerned about mass flux for the liner. And that is actually one of the big reasons that we use a forward finisil. So a finisil at the bottom is going to have a lot of mass flux once those fins burn off and touch the wall. But a finisil on the forward section of the motor sees almost no mass flux because we're only getting the mass that's traveling from the adjacent propellant, not all of the mass from the upper part of the motor slinging itself down and stripping away that liner wall. So this is an example of that, which is that while this section is different, while it's clearly burned a little bit more than the sections surrounding it, like this is soft and I can kind of feel the char layer a little bit more right here, there's basically no actual erosion. This is an almost purely cosmetic effect because there's no mass flux up here, and I guarantee if the finisil section had been closer to the nozzle, we'd see a lot more erosion. So this is an example of why we choose a forward finisil section.
One thing that's hard to see in this cross-section is that there is actually a hole in the linen phenolic which lets pressure pass through and get to the pressure transducer. This cavity and the transducer itself get packed with grease before firing. Grease doesn't really burn super well, and so it protects the sensitive electronics inside the pressure transducer from the hot combustion gases. Moving over to the microscope, I want to take a look at the O-rings on the forward closure because they are a mess. One O-ring here has some perfect squish, but the other one is filled with RTV in that cavity. I attempted the same sealing approach here as I did with the nozzle, which is to say that I coated the interface between the thermal liner and the closure with a bunch of RTV to try and create a tertiary seal. This ended up working against me though. I used too much RTV in this section, and the RTV extruded into the O-ring gap, which probably degraded the O-ring's performance, and there's definitely a hypothetical scenario where this actually causes more problems than it fixes. We certainly have plenty of RTV silicone in this gap to create that seal, but in the future I will want to use much less RTV here.
Finally, one of the last things that I want to look at is the erosion of the liner material. So this liner material was spun cast to basically 2 different dimensions. Ideally, it would all be 1, but it's quite hard to get the quantities right, and I messed up the density a little bit. The constrained dimension here is 0.375, and it should be pretty much on the money, if not a little bit off. And then as soon as the liner material gets past the spin casting cap, it's allowed to flow out this way. And we overpour on the ends, both A, because they see the most mass flux and they see the most heating, and B, because you want to really fill this section if you're going to try and do any sealing on this. So I would rather overpour on the ends and underpour in the middle.
The story is largely the same for the liner here. There's much less mass flux at the forward end of the motor, so the erosion that we see on this constrained section is functionally zero. I really overpoured the liner on this motor because I wasn't sure how fast it would erode, and now that I have that data, we can make a liner that is much thinner on the next motor. A thinner liner will let us pack more propellant into the same volume, which makes getting to space a little bit easier. I hope you enjoyed looking at these cross sections. There is so much to learn from looking inside this motor. It definitely sucks to cut open something you work really hard on, but the data is so valuable, and these cross sections are almost art to me. It's why I put them on a shirt like I mentioned earlier, and I'm kind of tempted to put these up as art in my house. If you made it to the deep end here, thanks a bunch for watching. Simplex V2 has been a long time coming, and my hope is that by sharing videos like this, you learn something that might be valuable to you if you're ever making rocket motors or maybe doing something else. Solid motor development is getting a little old, so let's pivot. In the next few months, I'm building a rocket that'll get up to Mach 3, test full 3-axis control just like the Space Shot, validate new approaches to telemetry and GPS solutions, and generally pave the way so that I feel good about building a massive 8-inch second stage early next year. As always, that project will take a little bit of time, and if you want to watch along in near real time, I make videos every 2 weeks on the BPS Patreon, and by supporting, you can keep the project going and get a little behind-the-scenes look before everyone else does. I want to give a huge thanks to the folks who support over there, and thanks to you for watching. I'll be back soon with another slammer of a video. May your skies be blue, and your winds be low. I love this clip so much. Boom!